In this lesson, we'll look at decomposition reactions. And a decomposition reaction is one where one compound splits apart into two or more pieces or simpler compounds or elements. So in general, if you have a compound C, it will break apart into different pieces, such as A and B. Now, most of the examples that we're looking at today are going to have one thing breaking up into two pieces, but that's not always the case for all decomposition reactions that exist. We're going to focus on two main types. One where binary compounds break apart into their elements, and one where compounds can break apart into other compounds. So for binary compounds, recall that a binary compound is one that is made up of two elements. The ones that we're going to be working with are going to be ionic compounds, such as aluminum iodide and mercury oxide. And they'll break apart into their elements. So aluminum iodide breaks apart into aluminum metal and iodine. And the big idea here is that you need to make the products the most stable form. So when you have your metal, it's just going to be the element itself, and that's going to be the formula, just the symbol for that element. Whereas the other piece, we need to pay attention to Hofbrinkel. So you need to consider the diatomic elements. So this is why the iodine is I2 in this case. In our mercury oxide example, we break apart into mercury and then oxygen. And what you're going to do is you're going to write the products and then you're going to balance the equation. And we'll do some practice shortly. For compounds breaking apart into other compounds, there are some important ones to look for. We're going to look at 4 different types within this category. We're going to look at compounds with carbonate, with chlorate. We're going to look at bases, so ones that have OH, and we're going to look at acids, ones that have H ions in them. And you'll see in the guidelines down here that I've summarized the rules that fit with these examples. So if we go through them one by one, a carbonate will give you an oxide plus CO2 when it decomposes. So this is an example here. We've got copper carbonate and it's being heated up. And what happens is we leave behind an oxide, so in this case copper oxide, and then the CO2 leaves. So the way that I think about this is I think, okay, it's got a carbonate, so I know that it's going to emit CO2, and then I'm going to make an oxide with what's left over. So my calcium is going to form a compound with oxygen. And we'll practice this later, but what we're always going to do is consider the formula by properly writing down the ions and crossing over. So for a chlorate, the rule is that we're going to get a salt and we're going to get oxygen. So I'm going to remove the oxygen from this and I'm going to make a compound with what's left over, with the K and the Cl. So again, K plus and Cl minus using the periodic table is how I know that it's Cl2. And then oxygen is O2 because it's part of Hofbrinkel. For bases, or compounds that contain OH minus, you're going to produce a metal oxide and water. So when they decompose, we release water, and then we form an oxide with whatever metal the base was made up of. So the formula here, Na plus and O2 minus, this is how I got Na2O. Acids, which have H in them, when they decompose, they produce a non-metal oxide and water. So HNO3 is an acid, it's nitric acid, and it produces NO2 and H2O. Now for these, knowing what the non-metal oxide is going to be is a little bit more challenging because there are different combinations of nonmetals with oxygen that are stable. NO2 is one, but I could also make NO, or I could make N2O5 or N2O4. These are all different oxides with this nonmetal. So as you'll see when we do an example, you'll be given information to help you to know what the oxide is going to be. So let's do some examples. Now, as we've seen, we need to be able to work with the formulas only to determine the products and write the balanced equation, and word equations. So for this one here, we have Ag2O. So looking at the options, this is a binary compound. So I've got a metal and a non-metal, two elements, and so it's going to break apart into its elements. The elements are Ag and oxygen. Because oxygen is part of Hofbrinkel, I'm going to produce O2. So you see how I write the products first, and then I'm going to consider the balancing. So to balance this one, I can see that I need a 2 for the oxygen and a 4 for the silver. With this next example, FeOH3, I can see that that is a base because it contains OH. So if I look at my rules, bases will produce a metal oxide and water. So I know I'm going to make water. It doesn't matter what order, so I can put the water first. And then on the side over here, I'm going to figure out what my metal oxide is. Because this is iron, it's a transition metal and has more than one charge. So I need to use this compound to figure out what the charge is on the iron. And I can see that it's 3+. I need to combine that with oxygen. So the ion for oxygen is O2-. I'm going to cross over and I make Fe2O3. To balance this equation, I'm going to balance the iron first. Put a 2 there. Next, I'm going to do the H. I now have 6H. So I'm going to put a 3 in front of the H2O. And I have a total of 6 O's, which is what I have on the left. The next one, nickel chlorate. I first need to figure out what that compound is. So nickel 2+. Chlorate is ClO3-. So when I do the crossover, I know that I have NiClO3 2. Now you'll notice in my balanced equation, I don't have any charges. So if you need to do the work on the side with the charges, you need to just put it over on the side. So when I have a chlorate, if I look at my rules, I am going to produce a salt and oxygen. So I'm going to release oxygen, and then my salt is going to be the compound with the nickel and the chlorine. So the nickel keeps its charge. Chlorine is Cl-, so when I cross over, I get NiCl2. And when we balance this equation, all we need is a 3 in front of the oxygen. I've got 2 chlorines here, 2 chlorines, 1 nickel, so all I need is a 3 for the O2. Next one, zinc carbonate. So zinc we know is 2+, and carbonate is 2-. So we start with ZnCO3. Carbonates release CO2, and then we need to make the oxide. So I've got Zn 2+ and O2-, so I make ZnO, and no coefficients are needed for balancing that one. My last one here, phosphoric acid. So first I need to name the acid or write the formula for the acid, and we have acids have H+, so I'm going to have PO4 3-. So because it's an ic acid, I need the phosphate, so I'm going to cross over H+ and PO4 3-, and I produce H3PO4. So that decomposes. Because it's an acid, it decomposes and makes a nonmetal plus water. So I'm going to produce H2O. And then this is what I was referring to earlier. To know what compound phosphorus and oxygen will make is not easy to predict. So you'll be given information so that you can do that. So diphosphorus, pentaoxide, P2O5. If I balance the phosphorus first, I'm still always following that same order. Elements other than hydrogen and oxygen, then hydrogen. So I have 6 hydrogens here, so I'm going to put 3 H2O. And when I look at the oxygens, I have 8 and 8. So we're all done.